Hello everyone, welcome back to our chemistry series. In today's class, we will explore a very important concept, shape of orbitals. This topic is crucial to understand how electrons are arranged in atoms and why elements behave the way they do in chemical reaction. So, by the end of this video, you will have a clear idea of how s, p, d and f orbital look and how they differ in shape and where they are used in electronic configuration. So first, we will start with understanding what are orbitals. An orbital is the region around the nucleus where the probability of finding an electron is maximum. Students often get confused between orbit and orbitals. So let's clear this once. In Bohr's model, orbit means a fixed circular path around the nucleus, just like planets revolve around the sun. Bohr believed that electrons move in these fixed paths without radiating energy. But in quantum mechanical model, we don't talk about fixed path. Instead, we talk about orbitals. So, orbitals is not a path, it is a region in space where the probability of finding an electron is maximum. So, the difference is simple. Orbits tells us fixed path, which is an old idea according to the Bohr's model. And orbitals tells us the reason of high probability of finding an electron, which is a modern idea of quantum model. We can remember it like orbit is like track and orbital is like cloud of probability. Probability. So orbitals are described by quantum numbers, which I have studied before, like principal quantum number n, which explain the size of the orbital, azimuthal quantum number L, which describe the shape of the orbital, magnetic quantum number M, which describe the orientation of orbital, and lastly, the spin quantum number S, which define the spin of electron. Now, let's explore the actual shape of orbitals. So, as we know, for L is equal to 0, there will be S subshell, which is spherical in shape. For L is equal to 1, there will be P subshell, which is dumbbell shape. For L is equal to 2, there will be D subshell, which is clover leaf in shape. For L is equal to 3, there will be F subshell, which is complex in structure. So let's start with S orbital, for which the value of L is 0. So S orbital is spherical in shape, in which electron cloud is equally distributed in all direction, but their sizes increases with increasing principal quantum number n. So here you can see the shape of the orbital is spherical, but the size increases with increasing quantum numbers. Here I am showing the shape of the s orbital, which is increases with increasing the value of n. Here you can see as the principal quantum number n increases, the size of the s orbital increases. So as the example which is given above, like in hydrogen, which has atomic number 1. So its electron goes in first shell. So here the principal quantum number n is 1 and the subshell will be 1s. In the next example, lithium, which has atomic number 3 and its electronic configuration is 1s2, 2s1. So last electron will go in 2s subshell. So here, the last electron goes in the second shell, for which principal quantum number will be 2. And in case of potassium, which has atomic number 19, its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Because this is the configuration of argon, so we can also write the configuration of potassium like argon 4s1. So here you can see the last electron goes to the fourth shell. So for this element, the value of N is 4. And when you arrange all these elements into increasing order of their sizes, then we will get these sequence like hydrogen, then lithium, then sodium, and then potassium. So size of s orbital increases with increase in principal quantum number n. Moving to the next, p orbital. For this, the value of L will be 1. It is dumbbell in shape, that is two lobes on opposite sides of the nucleus. And there are three orientation, px, py, and pz. Px, which is along the x-axis, py, which is along the y-axis, and pz, which is along the z-axis. And p orbitals are starts from second shell. Like in carbon, which has atomic number 6 and its electronic configuration is 1s2, 2s2, and 2p2. So we can see that p orbital start from second shell. This is the first shell K, and this is the second shell. So we can see that p orbital start from second shell. So here in this picture, you can see the orientation of p orbitals in three directions, px, py, and pz. It also explains the covalent bonding. So here you can see the orientation of p orbital in three directions, px, py, and pz. Like in oxygen, which has atomic number 8 and its electronic configuration is 1s2, 2s2, and 2p4. So here you can see in the p orbital, all four electrons goes like first electron, second electron, third electron. That is, first electron goes in px, second electron goes in py, and third electron goes in pz. And the last electron, that is fourth electron, goes again in px orbital with opposite spin. So if I am saying how many p electron can be present in one shell, then your answer will be 6, because there are 3 orbital and each orbital can hold 2 electron. Next is d orbital. For this, the value of L is 2. And this is more complex than s and p orbital. There are 5 orientation in space like dxy, dyz, dzx, dx square minus y square, and dz square. 4 of them like dxy, dyz, dzx, and dx square minus y square look like clover leaf. But the fourth one, dz square, looks like a dumbbell shape with a donut around it. And it starts from the third shell. So they have 5 orientation. 4 of them look like clover leaf shape, and the fourth one is like dumbbell shape with donut around it. Here you can see the orientation of d orbitals in different directions. So these 4 like dyz, dxy, dx square minus y square, and dxz. These 4 are look like clover leaf, and the fourth one, dz square, look like dumbbell shape with donut in the middle. So total 5 orbitals and each can hold 2 electrons. So maximum 10 electron it can hold. They usually found in transition metals. So transition metals are the best example to understand the importance of d orbitals. Transition metals are defined as the element that have partially filled d orbitals in their atom or in their ion, like iron, copper, nickel, zinc, etc. In this periodic table, blue color boxes showing transition metals. They are also called d block elements because their last electron goes to the d orbital. Actually, d orbital determine the d orbitals determine the property of transition metals. Like they show variable oxidation state, they are colored compounds. Just because D to D electronic transition which absorb visible light, giving transition metals beautiful colors. Their magnetic property, catalytic property, and formation of complex compound. These all are due to partially filled d orbitals. D orbitals. We will discuss it later in details. So you can think of d orbital as multi-pocket storage boxes. And transition metals use these pockets to keep or share electron. Because of this flexibility, they show different colors, magnetism, oxidation state, and form beautiful complexes. So if I am asking question like which orbital give color to the compound, like KMNO4 or copper sulfate, so your answer will be d orbital, which is due to d to d transition. D to d transition. Moving to the next, f orbital. For this, the value of L is 3. The shape of these orbital is very complex. It looks like flower with multiple lobes. It starts from fourth shell. Usually it is studied in higher chemistry, like in lanthanides or in actinides. So here in this picture, you can see f orbital have 6 to 8 lobes arranged in different direction. F block element in periodic table have two main sets, 4f and 5f. 4f orbital filled in lanthanides and 5f orbital filled in actinides. So these elements are in two rows and keep separate in the periodic table. Lanthanides are the element having atomic number 58 to 71 and actinide are the elements having atomic number 90 to 103. Lanthanides used in magnets, TV screen, lasers, and catalyst. And actinides are like uranium, plutonium used in nuclear power and medicines. So you noticed that how the orbital's shape evolved. As we move across the periodic table, the s orbital is just a sphere. This is s orbital, which is spherical in shape. Then p orbital bring us into double shape. With d orbitals, we start seeing clover leaf structure. Clover leaf structure. By the time we reach f orbital, the shapes are the most complex. So in the f orbital, multiple lobes of f orbitals are in different directions. This is It is almost like flower with multiple petals. This complexity increases because orbital must spread out in more direction to hold more electron. So today we learn about the shape of the orbital S, P, D and F. These orbitals are the foundation for understanding the electronic configuration, periodic trains and chemical bonding. If you found this explanation useful, don't forget to like, share and subscribe to the channel. In the next video, we will discuss how these orbitals combine during hybridization. Bye-bye.